In this lesson, we'll learn how we can use Hadoop to process very large amounts of data. For our exercise, we'll use a simple Apache access log to represent our big data. We'll learn how to write a MapReduce job to ingest the file with Hadoop and index it into Elasticsearch. When we need to collect, process, transform, and/or store thousands of gigabytes of data, thousands of terabytes, or even more, Hadoop can be the appropriate tool for the job. It is built from the ground up with ideas like this in mind. Using multiple computers at once, forming a cluster, so that it can process data in parallel to finish the job much faster. We can think of it this way. If one server needs to process 100 terabytes of data, it might finish in 500 hours. But if we have 100 servers, each one can take just a part of the data. For example, server 1 can take the first terabyte, server 2 can take the second terabyte, and so on. Now they each only have 1 terabyte to process, and they can all work on their own section of data at the same time. This way the job can be finished in 5 hours instead of 500. Of course, this is theoretical and imaginary, as in practice we won't get a 100 times reduction in the time it takes, but we can get pretty close to that if conditions are ideal. We also make it very easy to adjust the computing power when needed. Have a lot more data to process, and the problem is much more complex. Add more computers to the cluster. In a sense, it's like adding more CPU cores to a supercomputer. Your data grows and grows, so Hadoop must be able to easily and flexibly expand its storage capacity too to keep up with the demand. Every computer we add to the cluster expands the total storage space available to the Hadoop Distributed File System, or HDFS. Unlike other software, it doesn't just try to recover from hardware failures when it happens. The design philosophy actually assumes that some hardware will certainly fail. When having thousands of computers working in parallel, it's guaranteed that something somewhere will fail from time to time. As such, Hadoop by default creates replicas of chunks of data and distributes them on separate hardware, so nothing should be lost when the occasional server goes up in flames or a hard disk or SSD dies. To summarize, Hadoop is very good at ingesting and processing incredibly large volumes of information. It distributes data across multiple nodes available in the cluster and uses the MapReduce programming model to process it on multiple machines at once through parallel processing. But this may sound somewhat familiar to what Elasticsearch data ingestion tools do. Although they're made to deal with a rather different scenario, they may sometimes overlap a bit. So why and when would we use one instead of the other? First of all, we shouldn't think in terms of which one is better than the other. Each excels at the jobs it's created for. Each has pros and cons. To try to paint a picture and give you an idea of when we'd use one or the other, let's think of these scenarios. When we need to ingest data from billions of websites, as a search engine like Google does, we'd find a tool like Hadoop very useful and efficient. When we need to store data and index it in such a way that it can later be searched quickly and efficiently, we'll find something like Elasticsearch very useful. And finally, when we want to gather real-time data, like the price of USD or euros from many exchanges available on the internet, we'd find a tool like Logstash is good for the job. Of course, if the situation allows it, Hadoop and Elasticsearch can also be teamed up, so we can get the best of both worlds. Remember the scenario of scanning information on billions of websites? Hadoop would be great at collecting all that data and send it to be stored in Elasticsearch. Elasticsearch would then be great at quickly returning results to the users that search through that data. With Elasticsearch, you can think awesome search capabilities, good enough in the analytics and data visualization department. With Hadoop, you can think capable of ingesting and processing mind-blowing amounts of data in a very efficient manner and allow for complex, fine-tuned data processing. As mentioned, while tools like Logstash or even Spark are easier to use, they also confine us to the methods they employ. That is, we can only fine-tune the settings they allow us to adjust, and we can't change how their programming logic works behind the scenes. That's not usually a problem as long as we can do what we want. With Hadoop, however, we have more control over how things work at a much lower level, allowing for much more customization and, more importantly, optimization. When we deal with petabytes of data, optimization can matter a lot. It can help us reduce the time needed for a job from months to weeks, and significantly reduce operation costs and resources needed. Let's take a first look at MapReduce, which adds complexity to our job, but also allows for the higher level of control mentioned earlier. A MapReduce procedure typically consists of 3 main stages: map, shuffle, and reduce. Initially, data is split into smaller chunks that can be spread across different computing nodes. Next, every node can execute a map task on its received chunk of data. This kind of parallel processing greatly speeds up the procedure. The more nodes the cluster has, the faster the job can be done. Pieces of mapped data, in the form of key-value pairs, now sit on different servers. All the values with the same key need to be grouped together. This is the shuffle stage. Next, shuffled data goes through the reduce stage. This image exemplifies these stages in action on a collection of 3 lines of words. Here we assume that we have a simple text file, and we need to calculate the number of times each word appears within. The first step is to read the data and split it into chunks that can be efficiently sent to all processing nodes. In our case, we assume the file is split into 3 lines. Next come the map stage. Lines are used as input for the map, key, value, context method. This is where we'll have to program our desired custom logic. For this word count example, the value parameter will hold the line input, the line of text from the file. We'll then split the line using the space character as a word separator, then iterate through each of the splits, which are words, and emit a map output using context.write key value. Here, our key will be the word, for example, banana, and the value will be 1, indicating it's a single occurrence of the word. From the image above, we can see that for the first line, we get banana 1, apple 1, and mango 1 as key value pairs. The shuffle stage is responsible for taking key value pairs from the mapper and, based on a partitioner, decide to which reducer each goes to. From the image showing each stage in action, we can see that we end up with 5 partitions in the reduce stage. Shuffling is done internally by the framework, so we will not have any custom code for that here. The output of the shuffle stage is fed into the reduce stage. As its input, each reducer receives one of the groups formed in the shuffle stage. This consists of a key and a list of values related to the key. Here we again have to program custom logic we want to be executed in this stage. In this example, for every key, we have to calculate the sum of the elements in its value list. This way we get the total count of each key, which ultimately represents the count for each unique word in our text file. The output of the reduce stage also follows the key value format. As mentioned in this example, the key will represent the word and the value the number of times the word has been repeated. So let's dive in and do it. Wow, there's a lot of theory behind Hadoop, but practice will help us cement the concepts and understand everything better. So let's learn how to set up a simple Hadoop installation. Since Elasticsearch is already installed, the appropriate Java components are already initialized too. So we can verify that with java-version. And that should show you an output similar to this. OpenJDK is required by Hadoop, and on an instance where this is not available, you could install it with a command such as sudo apt install default-jdk. So now let's create a new user called Hadoop. Hadoop-related processes, such as the MapReduce code we'll use, will run under this user. Remember the password you set for this user, as it's needed later when logging in and when using sudo commands while logged in. We'll say sudo add user Hadoop. And I'll just set it to password so I don't forget it. And it doesn't really matter what we put in here. All right. So now we'll add the user to the sudo group to be able to execute some later commands with root privileges. Sudo user mod -ag sudo Hadoop. So now let's log in as the Hadoop user with su -space Hadoop. All right, we're in. So now we'll install the Hadoop binaries. Now note that for testing purposes, the commands that we're going to run can be left unchanged, but on production systems, you should first visit the Apache website for Hadoop and find the current stable version for Hadoop. Afterwards, you only need to modify the HTTPS links to point to the latest stable version and change text strings containing Hadoop 3.2.1 in our commands to whatever applies to you, as in change the 3.2.1 version number to the current version number if you're doing this in production. It's also a very good idea to follow the instructions regarding verifying the integrity of downloads with GPG and verify the signatures. But we'll just do it our way here. So while logged in as the Hadoop user, we'll download the latest stable Hadoop distribution that we know of right now using the wget command. Wget https downloads.apache.org Hadoop common, and right now we're at Hadoop-3.2.1 /Hadoop-3.2.1.tar.gz. Down it comes. We'll check back when that's finished. All right, that finished. So now let's extract the files from the tar archive compressed with gzip with tar-xvzf Hadoop 3.2.1.tar.gz. And once this is done, we'll move the extracted directory to user local Hadoop with sudo mv Hadoop 3.2.1 /user local Hadoop. So with the method we followed, the user local Hadoop directory should already be owned by the Hadoop user and group. But to make sure this is indeed owned by this user and group, let's run the next command, sudo change ownership -r Hadoop Hadoop user local Hadoop. Now Hadoop uses environment variables to orient itself about the directory paths it should use. So let's set these variables according to our setup with nano ~.bashrc. So let's scroll to the end of the file. And we'll add the following lines. Export Hadoop _home equals user local Hadoop. Export Hadoop install equals $Hadoop home. Export Hadoop MapRed home equals Hadoop home. Export Hadoop common home equals Hadoop home. Export Hadoop HDFS home equals Hadoop home. And export yarn home also to Hadoop home. And we will export Hadoop common lib native dir to Hadoop home /lib /native, and export path to $path Hadoop home /sbin Hadoop home /bin, and finally export Hadoop opts to "-d java.library.path equals Hadoop home /lib /native. There we go. Let's scan that real quick for any obvious typos. Looks good to me. So it should look like this at this point. And to quit the nano editor, we're just going to hit Control-X, type Y, and enter. Now to make the environment variables specified in the bashrc file take effect, we'll just say source ~/.bashrc, and that should be all set. So next let's configure the Hadoop properties. Hadoop needs to know where it can find the Java components it requires. Now we'll point it to the correct location by using the Java home environment variable. So let's see where the Java C binary is located with readlink -f $which Java C. And that actually didn't work because it turns out we don't have the full JDK installed. We just have the runtime environment set up here. If you say which Java C, it doesn't actually have one. So we need to fix that problem first. So let's go ahead and install the latest OpenJDK. And to do that, we can just say sudo apt install default-jdk. All right, so let's try that again. Now we have a Java C, and let's do that read link command to find where it really is. That's more like it. So in the case of OpenJDK 11, it will point to this path here. We're going to need to copy that path starting with /user and ending with OpenJDK-AMD64. So we're just going to exclude that bin Java C at the end. So we're going to paste it at the end of the last line with export Java home. So let's open up the hadoop-env.sh file in the nano editor, and we will add that path to the Java home variable. So sudo nano hadoop home /etc/hadoop /hadoop-env.sh. And we'll just scroll to the end of the file. Actually, there's a spot for it right there. Let's just put it there, huh? Export Java home equals, and I'll right click to paste that in. Don't need that trailing slash. And remember, if the OpenJDK version you're using is different, you will need to paste a different string of text after export Java home. Once again, we'll hit Control-X and Y and enter. And that will save the file. So let's test if our setup is in working order with Hadoop version. Cool. So we should see an output similar to this. It says Hadoop 3.2.1 and a bunch of other stuff. Looks like we're in good shape. So next, let's create our MapReduce project. So in this exercise, we'll index a sample access log file, which was generated in the Apache combined log format. We'll use the Maven build tool to compile our MapReduce code into a jar file. Now in a real scenario, you would have to follow a few extra steps. You would need to install an integrated development environment that includes a code editor such as Eclipse to create a project and write the necessary code. You would then compile the project with Maven on a local desktop and then transfer your compiled project as a jar file from your local desktop to your Hadoop instance. We'll explain the theory behind how you would create such a project, but we'll also provide a GitHub repository containing a ready-made, simple Java project. This way you don't have to waste time writing code for now, and you can just start experimenting right away and see MapReduce in action. Furthermore, if you're unfamiliar with Java programming, you can take a look at the sample code to better understand where all the pieces go and how they fit. So first, let's look at the theory and see how we would build MapReduce code and what is the logic behind it. So to get started, we would first have to create an empty Maven project using the code editor we prefer. Both Eclipse and IntelliJ have built-in templates to do this. We can skip archetype selection when creating the Maven project. An empty Maven project is all we require here. Once the project is created, we would edit the pom.xml file and use the following properties and dependencies. Let me bring up a screenshot of that. Some version numbers specified below may need to be changed in the future when new stable versions of Hadoop and Elasticsearch are used. The Hadoop-client library is required to write MapReduce jobs. So in order to write an Elasticsearch index, we are using the official Elastic Hadoop MR library. Commons HTTP client is needed too because Elasticsearch Hadoop MR uses this to be able to make REST calls to the Elasticsearch server through the HTTP protocol. So we'll define access log mapper and use it as our mapper class. Within it, we'll override the default map method and define the programming logic we want to use. Let's take a look at that code. As mentioned before, we don't need a reducer class in this example. Next, we need to define the Elasticsearch index. So here's a sample of what the log file looks like. So we've dealt with theory only up to this point, but here it's important that we execute this next command. So we're going to send a curl request to define the index in Elasticsearch. For the purpose of this exercise, we'll ignore the last two columns in the log in this index structure. So I'm going to go ahead and copy and paste this from my cheat sheet here, just so you don't have to watch me type it. But if you are following along, go ahead and hit pause at this point, and go ahead and enter this in yourself. Ready? Here we go. All right. Now having the datetime field defined as a date is essential here because it enables us to visualize various metrics using Kibana. Of course, we also needed to specify the datetime format used in the access log, which is dd, mm, yyyy, hhmm, ss, so that values passed along to Elasticsearch are parsed correctly. Next, we'll define our map logic. So since our input data is a text file, we use the textinputFormat.class. Every line of the log file will be passed as an input to the map method. Finally, we can define the core logic of the program, how we want to process each line of text and get it ready to be sent to the Elasticsearch index with the help of the ESOutputFormat class. The value input parameter of the map method holds the line of text currently extracted from the log file and ready to be processed. We can ignore the key parameter for this simple example. We split the line into separate pieces using the space character as a delimiter. Since we know that the first column in the log file represents an IP address, we know that the parts 0 holds such an address. So we can prepare that part to be sent to Elasticsearch as the IP field. Similarly, we can send the rest of the columns from the log, but some of them need special processing beforehand. For example, when we split the input string using the space character as a delimiter, the time field got split into 2 entries, since it contains a space between the seconds and the time zone in our log. For this reason, we need to reassemble the timestamp and concatenate parts 3 and 4. The ESOutputFormat class ignores the key of the mapper class output, hence in context.write at the end here, we set the key to nullwritable.get. Next, let's talk about the MapReduce job configuration. We need to tell our program where it can reach Elasticsearch and what index to write to. Let's take a look at that code. So we do that with conf.set es.nodes localhost 9200 and conf.set es.resource logs. Under normal circumstances, speculative execution in Hadoop can sometimes optimize jobs. But in this case, since output is sent to Elasticsearch, it might accidentally cause duplicate entries or other issues. That's why it's recommended to disable speculative execution for such scenarios. These lines disable that feature right here. And since the MapReduce job will essentially read a text file in this case, we use the textInputFormat class for our input. That's what the job.setInputFormat class line here does. And since we want to write to an Elasticsearch index, we use the ESOutputFormat class for our output with job.setOutputFormat class. Next, we set the mapper class we want to use to the one that we created in this exercise. And finally, since we do not require a reducer, we set the number of reducer tasks to 0. Now, once all the code is in place, we have to build an executable jar file. For this, we use the Maven shade plugin, so we would add the following to pom.xml. Let's pull in the finished project from GitHub. In case you don't already have Git installed on your machine, let's first install it. You can just do that with sudo apt update and sudo apt install git. Next, let's download our Java project with git clone https github.com Coralogix-resources /Elasticsearch with Hadoop mr lesson.git. So let's enter into the directory of this project. And we need to install Maven with sudo apt install Maven. And finally, we can build our jar file, mvn clean package. We'll see a lot of output and files being pulled in, and when the process is done, we should see a build success message. So we'll just wait for that to show up. And there it is. So now we can run our MapReduce job. Let's download the Apache Access log file that will represent the data we want to process with Hadoop. We'll do that with wget https raw.githubusercontent.com/linuxacademy /content-elastic-log-samples/master/access.log. Now let's copy the jar file we compiled earlier to the same location where our access log is located with cp target/es with mr -1.0-snapshot.jar and dot, and that last dot in the command just tells the copy command that the destination is the current location. Finally, we can execute the MapReduce job with Hadoop jar es with mr whatever it is .jar, and we'll pass as a parameter access.log. Off it goes. So when the job is done, the last part of the output should look similar to what you see here. Cool. So we should pay close attention to the MapReduce framework section here. In this case, we can see everything went according to plan. We had 10,000 input records and we got 10,000 output records. Now to verify the records are indexed into Elasticsearch, let's run the following command. Curl localhost 9200 _ cat indices $v. And we should see a docs.count matching the number of records under the logs index here. And there it is. So yep, 10,000 under logs. Perfect. So let's visualize this data with Kibana. Let's actually create an index pattern in Kibana for this. So let's go to a web browser. So let's open up this following address here. I'm just going to paste it in. So go ahead and pause and type that in yourself if you need to. And once that comes up, let's create a new index pattern named logs. So under index pattern, we'll just type in logs star. Success, that worked. And we're going to click on next step. And from the drop-down list titled time filter field name, we're going to choose date time and click on create index pattern. Cool. You should land on a screen like this. And in the left side menu, let's navigate to the Discover page. That's this little compass here. And we'll change our index to logs. Cool. And now let's set the time range from 16th of May to the 21st of May 2015. So we'll click on this and go to absolute. Change that to 2015, and we'll go in May 16th to, again, 2015, May 21st. And update. All right, there we have it. So the visualized data should look like this now. And from the available field section on the left, we can highlight HTTP status and URL and size. And we'll hit the add button that appears next to them. So now we only see the metrics we're interested in and get a much cleaner output here. Now since we have set the size property of the index to be of type integer, we can run filters based on the size. So let's view all requests that return data larger than 5 megabytes. In the search box up here, we could type size greater than or equal 5. How many zeros we got here? 6. 1, 2, 3, 4, 5, 6. And press enter. And above the bar chart, we can click on the drop-down list displaying auto and change that time interval to hourly. So now each bar displayed represents data collected in 1 hour. Cool, it worked. So let's clean up. Let's go back to our console and remove the index that we created in this lesson with curl-x delete localhost 9200 /logs. And we're doing this in the terminal window where we're still logged in as the Hadoop user. And from here, we can also remove the files we created, such as the jar file, the Java code, the access log, and so on. Of course, if you want to keep them and continue experimenting, you can do so and just skip the next command. But to remove all the files, let's go ahead and say cd and rm-rf Elasticsearch with Hadoop MR lesson. And finally, we'll remove the Hadoop installation archive with rm hadoop-3.2.1.tar.gz. Alright, so these are the basic concepts between writing, compiling, and executing MapReduce jobs with Hadoop. Although setting up a multi-node cluster is a much more complex operation, the concepts behind creating a MapReduce algorithm and running it in parallel, all on the same computers in the cluster instead of a single machine, remain almost the same.